Hello, thank you very much for the invitation. It's a real pleasure to be here. I'm Cora Dworkin. I'm an assistant professor at the physics department at Harvard here. And today I will be telling you about some work that I have been doing with my research group here on trying to solve fundamental problems in physics by using cosmological observations. So over here is a roadmap of my talk today. I will first start by giving you a brief background of the cosmic microwave background. I will tell you where we stand in cosmology today and what are the open questions right now. And then I will go into some of the questions that we have in fundamental physics today that we hope to shed light on by using cosmological observations. And since time is finite, I decided to choose one particular question, which is what is the physics that seeded the first structures in the universe? So I will be telling you about a general method that I developed in order to reconstruct the shape of the potential when the universe was a very tiny fraction of a second old. I will tell you how we developed a formalism, how we applied it to the data, how we ran Markov chain Monte Carlo likelihood analysis in order to infer the physics of the very early universe. And then in the last part of the talk, I will be telling you about how we can hope to learn about the energy scale of the very early universe by using the polarization of these CMB measurements. Okay, so since an important part of the talk will be based on me telling you how we can use the statistics of CMB fluctuations, I decided to first give you a brief background of this cosmic microwave background, which is the light, the afterglow that comes from the Big Bang. So let me start with a brief story here. In 1964, Arno Penzias and Bob Wilson, who is actually still a researcher here at the CFA, and you can see him around, were two radio astronomers working at Bell Labs in New Jersey. And they were trying to measure, with a horn antenna, they were trying to measure radio waves bouncing off balloon satellites. So in order to do their measurement and get rid of the interference that they had at the receiver, they were lowering the temperature using liquid helium. Now, they were facing an isotropic noise that they couldn't get rid of. They were trying very hard to get rid of this isotropic noise that wouldn't go away. I thought it was a myth, but since I've heard Bob Wilson tell this story, I feel confident to tell you this now. They even thought there were droppings of pigeons. They climbed the detector, they cleaned the detector, and of course, these droppings of pigeons didn't go away. So at the same time, Professor Jim Peebles, who is still a fantastic professor at Princeton, together with Dickey, Wilkinson, and Roll, were predicting a cosmic microwave background radiation that should come from the Big Bang. And they were starting to think about measuring this cosmic microwave background. A friend in common, Berkey, a professor and astrophysicist at MIT, told Penzias about the preprint that he had seen from Peebles. And this is where they start, the two groups that were not very far away from each other, Princeton, New Jersey, and Bell Labs in New Jersey, 60 kilometers away from each other, started to talk, and they realized, Penzias and Wilson realized that what they have discovered was actually not droppings of pigeons, but was the cosmic microwave background. And for this, they won the Nobel Prize. So since then, many different satellites some satellites were launched, and many different telescopes were built all over the world in order to measure the statistical properties of the cosmic microwave background. So the first of these satellites, known as COBE, the Cosmic Background Explorer, which operated from 1989 to 1993, measured two important things about the cosmic microwave background. First, it measured that the cosmic microwave background actually follows a black body radiation with a temperature of about 2.7 Kelvin. And the second important thing that this satellite measured is that they saw fluctuations around this temperature of about 1 part in 100,000. So this is how the map measured by the COBE satellite looks like, the map of our universe, okay? The different colors represent the different temperature fluctuations of the photons coming toward us. In red, I'm showing you our own galaxy, which is very bright, okay? And in general, it's masked. And the different colors correspond to different temperature fluctuations, 1 part in 10 to the 5, up or down 2.7 Kelvin, okay? So, in fact, COBE also won the Nobel Prize for this discovery. So later on, different satellites were launched into space. WMAP satellite that operated from 2001 to 2010. The Planck satellite that operated from 2009 to 2013, and actually we are still waiting for the final release of their data. Different satellites measure the cosmic microwave background fluctuations, and this is how the Planck satellite sees the temperature fluctuations. So what the Planck satellite sees is the temperature fluctuations in different parts of the universe, and cosmologists like me take this data that in general are made publicly available and use the statistics of this data in order to infer the physics from the very early universe, the composition of the universe, and its evolution. So these temperature fluctuations were measured to be Gaussian at first order and with a temperature of about 100 microkelvin. Okay, so this picture over here represents 13.8 billion years of the universe. As we all know, the universe began as a hot and dense plasma of particles in thermal equilibrium. It expanded and cooled, and many physical processes happened along the way. Some of them we know very well because we know our atomic physics, and some of them we actually don't know, and they are topics of, they are research topics in our community. So one of these processes happened about 400,000 years after the Big Bang, when the universe became cool enough in order that protons and electrons could combine into hydrogen atom. This process is known as recombination, although really it should be known as combination because it's the first time this happened, but okay, this is the way it's known in the literature. And so since then, the universe became neutral, and the CMB photons mainly free stream toward us until about 500 million years after the Big Bang, when radiation from the first stars and quasars reionized the universe. Now it's okay, the universe became ionized again, so this period is known as reionization. And about 7% of these photons rescatter, and this is the latest, this comes from the latest data from the Planck satellite. So today, we observe these photons at microwave frequencies and at a temperature of about 2.7 Kelvin. So if the field is Gaussian and isotropic, all of the information is contained in the power spectrum, okay? We can take the temperature fluctuations that we measure at different positions in the sky and make a spherical harmonic decomposition that I'm showing you over here. So by taking the 2-point function of these spherical harmonic coefficients, we can compute the temperature power spectrum. Now, the temperature power spectrum has been predicted and measured with great accuracy over the past 2 to 3 decades, okay? I'm showing you here the temperature power spectrum, or this temperature fluctuation squared, as a function of angular scale in the sky. In red, I'm showing you the data measured by the Planck satellite, and in green, I'm showing you the best fit model for this data. And you can see that it works very well. In this talk, we will be questioning some of the assumptions that are made in this best fit model in order to shed light on the physics that we still don't understand about these assumptions. So the structure, let me tell you a little bit about the physics that goes in the structure of these acoustic peaks. So the structure of these acoustic peaks carries the information of acoustic oscillations in the photon baryon plasma at the time of recombination. And I'm calling them acoustic oscillations because these are pressure waves, okay? Now, so this is what happens. What happens is that at the time, just before recombination, gravity was trying to compress the photon baryon fluid in potential wells created by the dark matter. And photons, as we all know, exert pressure. So photons were resisting this compression. And this resulted in acoustic oscillations, okay? The photon baryon plasma tried to go into the potential wells, and the photons were exerting pressure. So this resulted in acoustic oscillations. And this system is really equivalent to a mass on a spring falling under gravity. So this is a special topic that I give after in my Physics 15C course, where we study waves. After the whole semester of studying waves, we can absolutely, up to, at 0th order, we can understand the physics of the acoustic oscillations in the early universe. So these oscillations they have compressed regions that are hotter, rarefied regions that are colder. These oscillations were frozen at recombination because since then the photons mainly free streams toward us. So what we see is a snapshot of this time. Modes that were caught in an extreme of their oscillation represent peaks with enhanced temperature fluctuations, and the wave numbers of these peaks are harmonically related. There are basically two scales in the problem: the distance from us to the last scattering surface or recombination, and the sound, the distance the sound can travel by the time of recombination. Okay. Okay. So before moving on to trying to explain how we can use measurements of the cosmic microwave background and the large-scale structure of the universe in order to understand many of the open questions that we have in fundamental physics today, let me tell you where we stand in cosmology today. So we have a standard model of cosmology known as lambda CDM. We have a homogeneous background, and we measure the parameters of this background quite well. We measure them with the Planck satellite, with many satellites, with the WMAP satellite that came before, and with many satellites that are all over the world, the South Pole Telescope, the Atacama Cosmology Telescope, etc., etc. So we have learned that we have approximately 5% of ordinary matter, which is matter that makes you, me, this room, this country, this world, our galaxies, etc. Approximately 27% of cold dark matter, which is matter that we know it's there because we see its gravitational effects, but we cannot see it directly. And about 68% of a substance that we call dark energy, which is the substance that is responsible for the current accelerated expansion of the universe. On top of this background, we have perturbations, and we measure the parameters of these perturbations very well. We measure them to be nearly scale invariant and approximately Gaussian. So we made big strides in measuring all of these parameters. However, big questions remain. What is the lambda of our lambda CDM standard model of cosmology? What is dark energy? What is this substance? What is the CDM of our lambda CDM standard model of cosmology? What is the particle nature of dark matter? And what is the physics that seeded the first structures in the universe? So with my research group here at Harvard, we tackle mainly these three questions. But in order to be concrete, I will focus on some of the questions that we can ask regarding this main question, which is what is the physics that seeded the first structures in the universe? Okay, so as I told you before, we can use the CMB temperature fluctuations and the polarization fluctuations. The CMB is actually polarized, as I will tell you later on, in order to answer some of the major questions that we have in physics today. So for example, here are some. When did inflation happen? Inflation, as I will tell you, is a theory that tries to explain the physics of the very beginning of the universe. When did the first stars form? What is the geometry of space? What is the mass of the absolute mass scale of the neutrino? How many light relic particles are there? relativistic degrees of freedom that are beyond the standard model, what is the particle nature of dark matter, etc., etc. Okay, so let me jump into the more concrete part of the talk, which is I will base the rest of the talk in the question, what is the physics that seeded the first structures in the universe? So let me start giving you a brief background of inflation. Inflation is the main paradigm that explains the observed inhomogeneities in the universe today. It was proposed by Alan Guth, who is a professor here nearby at MIT. It is a period of accelerated expansion, and it explains why the universe is approximately homogeneous and spatially flat. Now, the condition of being a period of accelerated expansion implies that it is sourced by a component of negative pressure. Okay? This equation over here is basically the Einstein equations applied to what we call a Friedman-Robertson-Walker universe, which is a universe that is isotropic, homogeneous, and expanding. Okay? As we all know, it's happening with our universe. Okay, so basically the condition of being a period of accelerated expansion implies that it is sourced by a component of negative pressure. So the question is, what is this component of negative pressure? What causes inflation? And in the simplest models, this component can be taken to be a scalar field. We know different scalar fields in nature. We know, for example, a scalar field is a field that takes a scalar value. It's a function that takes a scalar value at different positions in space, okay? For example, the temperature field is a scalar field. The Higgs boson field is another scalar field that was recently, well, 7 years ago, discovered at the LHC. So in the simplest models, this component of negative pressure can be taken to be a scalar field. And now, it is commonly assumed that there is a single scalar field slowly rolling down the potential. This scalar field is known as the inflaton field, okay? So the equations of the background of this scalar field are given by the following set of equations. The dots here are derivatives with respect to physical times, and the primes are derivatives with respect to the field, okay? So here, h is the expansion rate of the universe, and this is the energy density of the inflaton field given by its kinetic energy and its potential energy. And the Hubble expansion appears as a source of friction in these equations, okay? So as the field slowly rolls down the potential, the comoving horizon is decreasing, and different modes of the quantum fluctuations of the field cross the horizon. Okay? The horizon is the measure of the part of the universe that, from which we can retrieve information. Okay? So what happens is that when a mode of this quantum fluctuation of the field crosses the horizon, a perturbation is frozen at a certain scale. So we can take the 2-point function of this perturbation and compute the primordial power spectrum that I'm showing you here. Okay? Now, a certain scale k, a wave number k, in this primordial power spectrum is associated with an angular scale in the sky that we can measure from the CMB temperature and polarization power spectrum. Now, what happens is that at different times, as time evolves, the perturbations are frozen at smaller and smaller scales. So the idea is that by measuring different angular scales or multiple moments in the CMB temperature and polarization power spectra, we can probe different areas in the inflationary potential. Okay? And since the physics of inflation is yet unknown, our goal here will be to shed light on the physics of inflation by using CMB observations. So, assuming inflation took place, it is important to remember that it's actually a theory. What are the questions that we can ask to shed more light on the physics, the physical processes that give rise to this period? Well, we can ask some questions. For example, here I gave you a list of some questions. This is not a complete list, but we can ask, for example, what is the shape of the inflationary potential? Are there additional degrees of freedom? This is a question that we have been also targeting with my group here at Harvard that I won't talk about it today. What is the energy scale of inflation? How far did the field travel? Did the field travel a sub-Planckian or a super-Planckian distance in field space, etc.? So in order to target specific questions in this finite amount of time that I have, I will focus on this first question and this third question over here. So let's get started. So I will tell you how we can probe the shape of the inflationary potential by using CMB observations, and I will define this inverse reconstruction problem over here where we start from the data and we try to address the physics of the very early universe, okay? So this is what is commonly done in the literature. In general, in the literature, people start from a specific model of inflation. From there, they solve the background equations, the Einstein equations, and the equations of motion of the K-modes of the inflaton field or the Mukhanov-Sasaki equation. They compute the power spectrum. Once we have the primordial power spectrum, we can evolve the Boltzmann equations for the different components of the universe and compute the temperature and polarization power spectra that is coming from that model. Compare it with the data and assess its statistical significance. Here, I will tell you about a method that I developed in order to reverse engineer and instead start from the observable CMB temperature and polarization power spectra, and from there impose constraints on the shape of the inflationary potential, okay? So let me give you, again, a little bit of a background for this formalism that then we will apply to the data, and we will have our inverse reconstruction problem. So let me give you a brief background of the standard way in which we are used to calculating, to describing the inflationary potential, okay? So the standard slow roll approximation is a commonly used technique for computing the primordial power spectrum for inflationary models where the scalar field potential is sufficiently flat and slowly varying. Okay, we can define what are called the so-called slow roll parameters given by time derivatives of the inflaton field. These slow roll parameters are assumed to be small, and they are linked to the shape of the potential. So under this approximation, we can compute the primordial power spectrum by evaluating the slow roll parameters at horizon crossing. However, by construction, this leads to curvature power spectra that are nearly featureless and almost scale invariant. And this is not necessarily the case. In fact, there have been claims of wiggles and features in the CMB temperature and polarization power spectra, generally from the temperature power spectrum since it's the best measured one, that gave rise to many, many models of inflation trying to explain these features. And models of inflation that try to explain these features in general have features in the inflationary potential. And these features could arise, for example, from a phase transition in the very early universe, okay? So years ago, I developed an approximation for models with large inflationary features that has a lot of nice properties. So the first nice property is that we can write the primordial power spectrum in terms of a single unknown function, which is what I will call the source function G prime over here, okay? And this source function is simply related to the local slope and curvature of the inflationary potential. So in taking the data and putting constraints on the source function, we can learn about the shape of the inflationary potential. We can recover the slow roll results for a constant source, and more importantly, this is well controlled, okay? So it leads to percent level errors when we have order unity variations. So let me tell you how we implemented this generalized slow roll formalism to the data, which is actually where the part of the talk that is more related to the topic of this symposium. These previous slides were a background to get to this part, okay? So with my excellent graduate student, George Soviet, here at the physics department, we decided to implement this formalism to the data. The most updated version of the data is the 2015 Planck data. We use CMB temperature and polarization data measured by the Planck satellite. We parameterized our source function in terms of a constant, okay, the source function will be given by this constant in the standard slow roll approximation, but plus we added this part over here that is non-zero if there are features in the potential, okay? So these are, this is a spline basis, and these are amplitudes in each bin of time, okay, of conformal time. So our model is the 6 standard lambda CDM cosmological parameters plus 20 of these spline basis amplitudes, okay? So we run a Markov chain Monte Carlo likelihood analysis with using CMB temperature and polarization data from the Planck satellite and varying these 26 cosmological parameters. And here are our results. So first of all, we computed the first, the most significant combination of these spline parameters in what I am showing you as the principal components of the covariance matrix of these spline bases, okay? So these are almost uncorrelated parameters, these principal components, and these first 3 are the most significant ones. So principal components are generally a nice basis to work with. They are easy to interpret. They are ordered in order of observability. The first one is the best measured one, the second best measured one, and so on. So in many of my works, I end up, for some reason or another, using principal components. So here you can see that out of these 20 different additional parameters, 2 of them, we saw that 2 principal components deviate from 0 jointly at the 99% confidence level, which is not very significant given that we added 20 additional parameters. So filtering the 3 first principal components, I'm showing you here the deviations of the source function with respect to slow roll over here. We can see a sharp suppression in power at about 300 megaparsecs. And we can also see that adding polarization data here, this suppression in power becomes sharper. So it can be better measured by adding polarization data, and this is for technical reasons. The transfer function of polarization has a more linear mapping between K and L. Now, we can also see that this general inflationary scenario shows a sharp suppression in the primordial power spectrum. Let's take a look at the shaded region that corresponds to 68 and 95% confidence level region. This is our reconstruction used from the data, trying to be as model independent as possible of the primordial power spectrum that gave rise to the seeds of matter in the universe. So we see a sharp suppression over here at scales of about 4 times 10 to the minus 3 inverse megaparsec. Now, even if you don't care about the very early universe, which would be hard to believe, but okay, some people don't care about it. Even if you don't care about that, and you care about the late universe, this is also important because cosmological parameter inferences depend on the shape of the primordial power spectrum. So here, for example, I'm showing you how evidence for features beyond lambda CDM in the temperature data have been claimed. So evidence for features in the beyond lambda CDM have been claimed in the temperature data. Tensions in the late time cosmological parameters have also been claimed. And here what I'm showing you is that there is a way to link the 2 of them, okay? So in particular, I'm showing you the probability distribution function of the Hubble constant, which is a parameter that tells us about the current expansion rate of the universe. And so we can see, let's take a look at, first of all, let's take a look at the black curve and the red curve. So here we just took lambda CDM scenario, okay? Slow roll inflation, single field. We divided the data for L less than 1,000 and L and the full data set. And we see that there is some disagreement between the probability distribution for the full data set in black and for multiples less than 1,000 in red. Now, what we pointed out in this work is that local cosmological inferences depend on the assumption of the shape of the inflationary potential. And in fact, if we consider a general inflationary scenario, we can we can very well recover low values of the Hubble constant. Okay, and this is because when we add a general inflationary model, in particular with the data set that we observe in the universe, we can fit the suppression in power at large scales. This allows us to have a larger cold dark matter density, which pushes the Hubble constant to have lower values. Okay, these two are anti-correlated. Now, why this is important? Well, even if you don't care particularly about the expansion rate of the universe today, this is important because this is one of the current outstanding problems in our lambda CDM standard model of cosmology, okay? There is a well-known tension that right now is more than 3 sigma tension, which for cosmology is a lot, between measurements, inferences that we make about our Hubble constant coming from CMB observations, and local measurements of the Hubble constant done with local measurements, for example, done using supernovae data. Okay, so these are measurements made by Adam Riess, who you probably all know. He was a graduate student here and won the Nobel Prize in 2011. These are measurements that he keeps doing over and over with different people and different groups, keep doing by using supernovae data, and they keep getting a Hubble constant that is larger than the Hubble constant inferred from CMB observations. So at the moment, taking at face value the numbers reported by Adam Riess in his latest paper, this tension is about 3.8 sigma, okay? So either there is a systematic in the CMB measurements, there is a systematic in measurements, in local measurements, or there is the possibility that this is pointing to new physics. For example, new additional relativistic degrees of freedom, a sterile neutrino, who knows? So this is a topic of active exploration in cosmology. Okay, so with this, I will slightly transition to the second part of the talk, which is related, which is now I will tell you how we can use CMB polarization measurements in order to continue to learn about the physics of inflation. But in this part of the talk, I will be asking the question, can we probe the energy scale of inflation? Okay, so let me stop for a second and give a brief review of CMB polarization, okay? So CMB is linearly polarized. It's actually the temperature quadrupole that each electron sees along the line of sight, which sources CMB polarization, okay? So polarization is generated by Thomson scattering of photons of free electrons. And once we have a measurement of the polarized signal in the sky, we can decompose it into what we call E modes and B modes. E modes and B modes are the tensor analogs of curl-free and divergent-free components of a vector field that we are all very familiar with from electromagnetism, okay? So for example, the E modes have their direction, they are radial around cold spots and tangential around hot spots, and the B modes have their orientation rotated by 45 degrees with respect to the E modes, okay? So what is important for the next part of the rest of the talk is that when we have linear sources, scalar sources, and linear evolution, we can generate only E modes, okay? To generate B modes, we can so B modes can be generated either by having gravitational lensing due to massive structures along the way that deflects the path of the photons coming from the last scattering surface toward us in Earth, or by having potential primordial gravitational waves that distort space-time and create CMB quadruples that source CMB polarization, okay? So so here I'm showing you the B-mode power spectrum as a function of angular scale or multiple moment in the sky. This corresponds to large angular scales. This corresponds to small angular scales. Scattering of photons of free electrons during the epoch of reionization generates a band at large angular scales. Scattering of photons of free electrons at the time of recombination generates this other bump in the B-mode power spectrum from gravitational waves at smaller scales. Okay, these are scales that are targeted by experiments like BICEP, for example, whose PI, who's one of whose the people working in an important part of the BICEP team is here at Harvard. Now, in black, I'm showing you the gravitational lensing power spectrum, the B mode coming from gravitational lensing. And so these are the main sources of B modes. And now the current milestone in the field, one of the current milestones in the field, is to try to have a measurement of these primordial gravitational waves that have not been detected yet. Okay? Now, where are these primordial gravitational waves coming from? So, in addition to scalar modes, inflation also predicts a nearly scale invariant power spectrum of gravitational waves. And a measurement of this tensor contribution would provide a direct measurement of the expansion rate of the universe at the time of recombination, as well as its energy scale. So for example here, I'm showing you how if we were to measure the tensor to scalar ratio, denoted with this R over here, to be greater than 0.01, we would be probing energy scales that are energy scales that correspond to the grand unified theory energy scales, okay? And vice versa. So a potential detection of primordial gravitational waves would open a window onto the physics of the very early universe and provide us with additional information about this early universe. So this, first of all, let me state that this relic would constitute our most direct probe of the very early universe and transform really the way we understand the very early universe in outstanding ways. So for example, because the signal is originated from quantum fluctuations of the space-time, if we were to detect these primordial gravitational waves, this would provide us insight into the quantum nature of gravity, which is one of the major puzzles that we have today. It is also a unique window into the highest energies that we will ever be able to probe. Not that we probe right now, but we will ever be able to probe, okay? Scales of the grand unified theory, so 10 to the 16 GeV, correspond to 10 to the 12 times high energy scales that are 10 to the 12 times higher than the energy scales that are probed at the Large Hadron Collider, okay? These are really the highest energy scales that we can ever probe. So how do we know if a B-mode measurement is primordial or not? So over the past, say, 5 years, we have learned that actually the foregrounds in our universe, in particular dust polarization emission, contributes also to a B-mode signal that we need to take out of the way. So it is obviously important to make sure that if what we are measuring is primordial. So in order to do that, we make, the goal is to use maps at very different frequencies to try to disentangle the CMB from the different foreground components, okay? So we can see here the different frequencies, the different polarized maps measured by Planck. Galactic synchrotron emission is strongest at lowest frequencies. Galactic dust emission is strongest at the highest frequencies. And the CMB is mostly uncontaminated at mid frequencies and at high latitude, okay? So let me tell you 2 ways. How much time do I have? 5 minutes. Very quickly, I will tell you 2 ways in which we are hoping to target this problem, okay? So the first way is by making a multi-component, multispectral likelihood analysis. So I developed code to explore, with the Markov chain Monte Carlo likelihood analysis, a possible component of gravitational waves plus foreground components such as an amplitude and the spectral and frequency indices, spatial spectral index and frequency index. We marginalize over all these components, and we use, in particular, back in the day, I used BICEP and Keck data together with Planck data at different frequencies. And these were not our results. These are the latest version of the results of the Bicep-Keck collaboration, okay? Here you can see the probability distribution function for the tensor to scalar ratio and the probability distribution function for the different foreground components. Since I'm a cosmologist, I'm mostly interested about the physics of the very early universe, but astrophysicists also care about the parameters that describe the foreground. So we learn that the tensor to scalar ratio is less than 0.07 at the 95% confidence level. So the quest for gravitational waves will continue. Here's where we stand right now. There is this proposed experiment, a proposed next generation experiment called CMB Stage 4, in which a big part of the cosmology community, including myself, are working hard on. I'm currently leading the inflation group on this CMB Stage 4 proposed experiment that will be able to give us a lot of information about different questions. Some of them I showed you at the very beginning of the talk. In particular, in terms of the tensor to scalar ratio, or the amplitude of the gravitational waves, we will be able, having now 100,000 detectors, we would be able to probe the tensor to scalar ratio to values of about 10 to the minus 3 to 10 to the minus 4. Now, another way, and let me finish, I probably have 1 minute or 0 minutes. Okay, the last point that I want to make is that I wanted to advertise some work in progress that I have been doing with 2 former undergraduate students, Sebastián Wagner Carena at the physics department, Max Hopkins actually at the math and computer science departments here at Harvard, and Ana Diaz Rivero, who is an excellent graduate student here at the physics department. We have been going beyond these template fitting techniques and trying to use a blind source separation technique, okay, in which we express the data as different sources times a mixing matrix that has information about that has the frequency information of each source plus the noise of each data set considered. And each source is some independent component of the signal in the sky. And to make the algorithm more efficient, we are using a wavelet basis to describe the sources in a sparse way. And the goal is that given a set of measurements and an estimate for the instrumental noise, to get the best fit that minimizes the CMB variance for the mixing matrix and the sources. Okay, so basically the idea is to, given maps at different frequencies, try to separate out the CMB signal, just having the frequency information. Okay, so this is what we call hierarchical generalized morphological component analysis. This stands upon previous work by a French group. And these are our current results of the CMB. This is the input CMB map. Sorry, this is the input CMB map, and this is the reconstructed CMB map. We can see that we can reconstruct it quite well. This is just work in progress, so stay tuned for this new way of trying to get the CMB map from blind source separation analysis and then try to recover the tensor to scalar ratio. So with this, let me conclude. I told you in the first part of the talk how we can use CMB observations in order to reconstruct the inflationary potential, so to do inverse reconstruction from the data. I also talked about the energy scale of inflation and how doing statistical inference, Bayesian inference, we learned that the tensor to scalar ratio is less than 0.07 at the 95% confidence level. Many more measurements will come over the past decade, okay? The Simons Observatory, CMB Stage 4, et cetera, et cetera. There are many experiments that are currently taking data and being planned. So we will learn more about gravitational waves soon. And machine learning techniques are expected to excel in many of these different questions that we have. In particular, here I was telling you about the question of the trying to reconstruct the foreground contribution, but more generally, machine learning techniques could help improve constraints and fundamental physics parameters. With Anna, we have been trying to use convolutional neural networks in order to learn more about the particle nature of dark matter. So this is something that definitely needs to, this is a technique that has been used by the cosmology community, but definitely needs to be further explored. So stay tuned to what the next decade has to tell us. Thanks.
Let's see. Take a question. I guess we'll have to wait for the next decade to see how
Okay.
Machine learning can be employed to answer some of these questions. Okay. Yeah. Why don't you ask her?
Yes.
I didn't understand. Do you really do the inverse problem, or you do a generating model and evaluate the confidence, and from there you get the inverse? You don't start from the data and inverting it as such. Maybe I misunderstood.
Well, I'm starting from the data. I assume a lambda CDM model plus this general inflationary model. That's a generating model, and then I try to, yes, so it depends on how you, what you're calling, so what I'm calling inverse reconstruction is just the fact that I'm starting from the data and I'm trying to inverse reconstruct the physics that I'm not assuming.
Yeah, I mean, it seems like you're generating model, you evaluate, evaluate. Have you tried to start with the data, evaluate the loss function, the cost function, likelihood, take the derivatives with respect to the parameters to see what you see, which would be the more traditional inverse problem.
And take the derivatives with respect to the parameters.
And then construct the actual thing there.
This is very close to what I'm doing. We can discuss it further, but so basically, so we can discuss it further. I'm not sure I'm understanding your distinction, but what we are doing is basically taking the data and inversely trying to assess the statistical distribution of these parameters.
Okay, I think we need to move on in the interest of time. So I'd like to thank Cora again. And